Hello, this is Concrete Path. Today's lecture is about the problems that we have related with the torsion of those shafts. So let's have those shafts. So the first one is that you have one. You can say this is some beam, or we can say this is some shaft, beam or a shaft. Then after that you have one sort of normally we say that this is your normally projecting horizontal beams. So we had that projected two beams. So they are in the z direction. You can say this is z direction, this is x direction, this is y direction. So they are having a load of p, and this one is having a load of 2p, and the distance is that lever say that lever arm is equals to a, and the distance between the support and this load, that is 2a, 2a, and 2a. So you need to say draw those diagrams of shear force, bending moment, and torsional moment. Let's go solve that. So if we make the free body diagram, let's say that this is some load P, and here it would be some reaction of P, and there would be some moment developed, M equals to P into A. Similarly, for this one, you have 2P, and there would be 2P, and the moment developed would be equals to 2PA, and same would get transferred on the main beam, Let's say this one. So here the moment developed is equals to clockwise. And in this one, moment developed would be anti-clockwise. So let's say this is anti-clockwise moment. And similarly, here the moment was clockwise. In the next one, similarly here it would be anti-clockwise. This is anti-clockwise. So anti-clockwise moment. But here the moment it is not a moment on this beam, because it was moment developed for this lever or bracket. For this bracket it was developed a moment. But if you see this moment in the long axis, it's a torsional moment. I would say this is mx. So moment in x direction. So this is some moment t. I would call it as a torsion moment. T equals to PA, and this one equals to torque equals to 2PA. So this is some T1 and this is some T2, 2PA, and a load is also there, because of this reaction, P, and same would get transferred in the opposite direction on the main beam. This is some P. Similarly here there is some 2P. So we got the main loading on our main shaft, our main beam. So let's have that now. Yeah, we can solve that now. Let's take that in a separate way. Let's say the torsion, we solve it for in a separate way, and for the loadings we solve it for separate. Let's some sort of torsional moments where we are applying anti-clockwise, so that is PA, and this one is also anti-clockwise 2PA, and we can solve those. Let's have this one. Here the length is 2A, 2A, 2A. We know that those fixed end moments that get developed. If you have that cantilever beam, you apply a load of P at a distance of A and at a distance of B. So then the moment developed here equals to PA B square by 8 square L square. L is your A plus B, and similarly from this side we have PA square B by L square. Do you know that? We have checked it for, I think, in the moment area method. We might have touched it in the moment area method. So based on that result, we can have those superposition of those two loads. We can solve for the moment at A. Let's say this is support A and this is your B. I would solve that moment at A. moment at A equals to, let's solve for the first one. P into 2A into 4A whole square by L square. And there is one more moment of that 2P and length of 4A, and then after that 2A square by 6A whole square. So this is the equation. And similarly for the moment B, that is equals to, let's solve for this one first. That's P into PA square, that is 2A whole square, and after that 4A, 2A square B upon L square, 36A square, plus then after that 2P and A equals to 4A. A equals to 4A. After that you have 2A divided by 6A whole square, and you solve those and you get some moment. You would get some moment of this one equals to some sort of values. We have solved those and they come out to be equals to 16 by 9 of PA, and this one is that 20 by 9 of PA, and there was some loading of P here and a loading of 2P at this location. Now we want to say the reactions, get the values of reactions. Let's say this is some reaction A and there's some reaction B. Let's apply that summation of moments on either of the sports. Let's say summation of moments at B goes to 0, and I will write anti-clock is negative. So I write 16 by 9 PA square minus times. Then after that we have P into 4A minus 2P into 2A, and we have clockwise 20 by 9 PA, and we have the reaction A into 6A. So we have that reaction A into 6A. So we solve that and we get some reaction A comes out to be equals to 34 by 27 of P. And similarly, we can get B value equals to 3P minus A, that comes out to be equals to 47 by 27 of P. So we got those reactions, and we can get the values of the SMT. We can solve for the SMT now. 34 by 27, and we have this one also. So let's have that SMT. So this is your general loading, and we want to get the SMT. So let's have that SMT. So we have to go 34 by 27 upwards, 34 by 27 of P upwards. After that, there is a decrease. That's 34. Then you have to subtract this value, and you get a net value of 7 by 27. 34 minus 27, that is 7 by 27 of P. So you got this value of net value of 7 by 27. Then after that, it decreases by 2P. So you got a final value such that it is equals to reaction at B. So you got a minus 47 by 27 of P. And this is your SFD. This is your SFD. And now you want to get the PMD. You want to get the value of PMD. Let's have the BMD. I would say you are applying an anti-clockwise 16 by 9 PA. Then there is a linear variation. I would say the bending moment diagram would be a linear variation, such that the value of moment here would be equals to PA 16 by 9. This is negative, and I have to add that area of that SFD between the 2 points. I would write 2A into 34 by 27 of P into A. Yeah, we got the sum value that comes out to be equals to 20 by 27. Let's say this is 20 by 27 of PA, and I can join those 2 points. So we got this value. Similarly, after writing that new moment plus that area between the 2 points, we would get some value increased. Finally, we get some bending moment diagram in this fashion. I would write this value would be equals to this is 34 by 27 of PA. That is equals to 20 by 27 of PA plus area of the SMT between the 2 points. That is 7 by 27 PA P into 2A, and you would get this value. And after that, this value we can say you subtract that from this one and you would get a value of 0. So this is your BMD. And by the linear, by say that those similar triangles, you can get the value of that POC. And after that, you have that TMD. You need to get the value of TMD. You need to draw that TMD. Now let's have the line diagram. Your moment is clockwise about that long axis, polar axis. So your thumb points towards the support A, I would say. So this is support A. I would say this is some moment of PA, and this is some torque of 2PA, and there would be some balancing torque, and there would be also some balancing torque. Let's say the direction is, this is some TA and this is some TB. I would write TA plus TB equals to 3PA. I would write that in this way. And we have that compatibility. We have that compatibility condition that between the two fixed supports, I would say theta total would be theta A equals to theta D, theta B equals to 0. That is equals to, let's say this is A, B, C, D. I would write that theta AB, theta AC plus theta CD plus theta DB goes to 0. And now I want to say what is the value of different torques we have in this section. I would say this is some torque in the same direction we are going. So this is some TA. This is some TA. After that, there is some decrease. There is some decrease. Let's say that decreases by amount of. Let's make in terms of only. Let's say that TA is more. Let's say TA is more. Assume. Let's say it's more. I would say that there is some bigger value of TA, and you go, and there's a decrease of T. There is a decrease of TA by amount of PA. I would write net value comes out to be equals to TA minus PA. After that, I would say it would also decrease once more. So final value would be TA minus 3PA. TA minus 3PA. And there would be net value of, here we have that finally TB. I would say no, that this value should be, yeah, I would say this, we got some value. Yeah, so it's not matching the BMD. It's that at the end the SFD would increase in this way, that at the end we have the TB in the same direction as that of the traverse. So if you are going that way, I would say you are going that way, that means it will increase, that SFD won't come to 0. That what we call as TMD won't go to 0. So to make the things easier, I would say the TB should be in the opposite direction. Let's assume that TB should be in the opposite direction. Then that means I would write TA minus TB equals to 3PA. If that is possible here, I would say let's have that final value, that this is some value of TB. This is some value of TB. Yeah, this is some value of TB. Then I would write TA minus 3PA equals to 3, that TB. I could write that TA minus TB equals to 3PA. That is the equation we have already got from that force equilibrium, I would say. I assumed that initially the direction of TB is in this direction, but from the diagram we have DMD. I said that there is a chance that TB would be in the opposite direction. Then this is one possibility. You can solve for this one. Now you can solve for this one. Let's have this one now. If I solve in this way, we have the lengths of 2A, 2A, 2A. We have the lengths of 2A, 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 and your TMD is positive. I would write for the theta 1, I would write TA L by GJ plus, next one is that TA minus PA L by GJ plus, the third one is that TA minus 3PA 2A by GJ, and that goes to 0. And I would got a value of TA plus TA minus PA plus TA minus 3PA equals to 0. So net value that 1 TA, 2 TA, 3 TA. So I got a value of 3 TA equals to 1 and 2. So we got a 4 PA. So I got a value of TA equals to, TA comes out to be equals to 4 by 3 of P into A. So your torque developed at A, that is a positive value. That means the direction you assume that the direction of that TA, you assume that the direction of TA is in this direction. That means in this way your moment developed, torque developed is in anti-clockwise manner. Anti-clockwise, I would say, in this way. Your torque developed is in this way, that in this way. This is your torque developed. This is your torque developed about the polar axis. So you got the TA value of 4 by 3 PA. That means value of TB should be equals to, value of TB should be equals to, TB should be equals to TA minus 3 PA. That is equals to 4 by 3 minus 3 of PA. That's 4 minus 3, 4 minus 9. That's minus 5 by 3 of PA. That means the direction you assumed, we assumed the direction of PA is, we assumed the direction of PA that was I said the direction of TB should be in this direction, because there should be the decrease of TB downwards. So I assume the direction of TB is in this direction, but you got a negative value. That means the TB, it should be equals to positive 5 by 3 PA. That means the direction should be in this way, the same direction of that TA. Now one more thing is that if you want to take the TMD in the other way, if you want to take this TMD in the other way, I would say this is a reference line. I would take that this is some value of TA. After that, there is some decrease of that final value would become, let's say that TA is lesser than PA. Let's say that TA is lesser than PA. That means PA is more. If PA is in the opposite direction, negative, I would say it would decrease. So final value would be some value of PA minus TA, PA minus TA. So then after that, it would remain constant. And there is one more, there are 2 PA coming. So if I have that one also, I would go one more time, that I would write 3 PA minus TA, and that we have final value, and that would be, and then I have to assume that, see, to make the final TMD comes to 0, I had to ensure that there is a positive, that there is some value of TB such that its arrow is in the same direction of traverse. So there is some TB in this direction. So as that, initially I assumed that TA is in this direction and TB is also in this direction. Then I wrote that TA plus TB equals to 3PA. These were in this direction, and 3PA net value was in the opposite direction. So if I take that way also, you can solve that way also. So for that, in that case, you have to take this one positive, this one, these two negative. Then we have to write TA L by GJ plus minus times PA minus TA, and L is same for the 3 sections. After that, third one is that 3PA minus TA, then it's also negative, and 2A times that equals to 0 divided by GJ. So you got the same, you would get the same value, and here you get a value, you would get a value of TA was equals to 4 by 3 of PA, and but the thing is that TB you would get a value of TB equals to 5 by 3 of P into A. That is a positive. That means the direction of TB would be in this direction. So you got this one also. Now you want to make the TMD now? Can you make the TMD now? Can you make the TMD now? Let's go. Let's make the TMD now. So you got this one. You had that reaction. You had that reaction of TE. You had that reaction of TB, TA. That was equals to 4 by 3 of P into A positive. Based on that, we have this arrow, and we have also this arrow, and we have this one and this one. So this was your 4 by 3, this was your 1, this was your 2, this was your 5 by 3. So let's have those values. 4 by 3 minus 1, that would be 1 by 3. This is 1 by 3 of PA. After that, you reach to this point, that then we would say 1 by 3 minus 2. That would be equals to minus 1 by 3 minus 5 by 3 minus 5 by 3 minus 5 by 3 PA. After that, you have this 5 by 3, so net value comes to 0. Net value would be 0. So this is positive, positive, positive. This is TMD, final value of TMD. So we got this problem. Now let's take one more. Let's take the another problem we have. Let's take the another problem we got here. We got this one. Let's have the other one. 7. So we have two shafts. We have two shafts. One is your solid shaft, and the diameter is D. And next one is that you have a hollow shaft. 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 You have a hollow shaft such that I would say the mean diameter of that hollow shaft, that is equals to D. So the mean diameter would be, let's say this is D inner, and let's say this is D outer. So I would write D outer plus D inner by 2, mean diameter, and there is some mean diameter. That's some mean diameter, dm. Let's call it as dm. So this is given. One more thing is that you have the material same. These two shafts are of same material. That means tau max is same. Same material. That means tau max is same for both the materials. And you need to say, and the question is saying for the same weight of the material, for the same weight of those shafts, for the same weights we need to say for the same weights you need to say the ratio of the torque transmitted, ratio of those torque transmitted ratio, and you need to say that angle of twist angle of torque ratio also. For this condition that you have to take the same weight. Now you got this one. And you need to say for the torque transmitted ratio. So if you have the torque formula, do you know that what is the value, what is the ratio, that equation for torque? We have that equation that tau by j equals to tau by r, t by j goes to tau by r equals to g theta by L. So till now, for the first case, I would say ignore this part. I would be using this part. We have torque and we have shear stress of tau. For that, you need to say you have two different shafts. Let's say that we have solid shaft. I would say solid shaft torque, and J solid equals to tau. Tau is same, tau max is same. And what is the value of R at the rate of tau max? At the rate of tau max, you have to take R equals to capital D by 2. So I would take that diameter by 2. The diameter we have here, we have that diameter D, and I can take capital R. That capital R goes to D. Small r goes to that diameter by 2. So this is tau variation. Let's have that D by 2. And we know that the value of J would be equals to pi d power 4 by 32. So you got a value of that T solid equals to tau max by 16 times pi d cube, 16 t power pi. We have that equation 60 t upon pi d cube, that is tau max, 16 t upon pi d cube. So let's write that pi d cube. So you got this equation of ts. And similarly for the hollow section, we have that equation that tau max equals to 16 t upon pi d outer cube and 1 by 1 plus beta power 4. Do you know this equation? We have this equation. 1 plus beta, 1 minus beta. Oh yeah, it's 1 minus beta. 1 minus beta. We have this equation of 16 t upon pi d outer cube 1 minus beta power 4, while your beta value equals to d inner by d outer diameter. So you need to say what is the difference? What is the value of d outer? Because we got here a value of d outer, but in the other one we have only a value of d. So you need to convert one of the two into other one. So we have the condition given that the d mean equals to d outer, d mean equals to d outer plus d inner by 2. Yeah. So d mean is equals to d outer plus d inner by 2. And if I have one more thing here, that's that for the same weight we have the same weight material. For the same weights, we have to say what's the ratio of the torque transmitted. So if we have same material and we have same weight, I would say you have weight equals to gamma into volume, gamma into volume, gamma equals to weight by volume, weight upon volume, mass per unit volume, I would say. So if your gamma is same, then volume is also same. Yeah, volume is also same. Volume is also same. No, you have same weight, same gamma. That means your weight is a function of volume. Weight is a function of volume, I would say. Weight is a function of volume. If you have weight is a function of volume. That's area into length. Area into length. If you keep the length same, if you have those shafts, length the same, length hollow, and length I would say length solid. Length solid equals to length hollow. That means you have to change the area. I would say your weight, for the weight, same weight, you have to take areas, you have to change the area such that overall volume is constant. So if I take that area, that area hollow, area solid equals to area hollow. So we have the area solid equals to pi by 4 d square, and we have that hollow area equals to pi by 4, and the area between, we have the hollow area. How can you solve that? We have this area only. I would say I would take that outer minus inner. Can I take? We say that in this way: pi by 4 d outer square minus pi by 4 d inner square. So finally you got a value of d square equals to d outer square minus d inner square. And one more thing is that if I can simplify it, I would write d outer minus d inner plus d outer minus d inner. Can I write it in this way? D square equals to d naught square minus d inner square. Now one thing is that we have that I wrote that one thing, that one more condition is that given that d mean was given to you, that is equals to d. The d mean was given to you, that equals to d. That means this part equals to d. This part goes to d. So if I write that value of if I write this value here, that means I would write d outer plus d inner by 2 whole square equals to and that equals to d outer minus d inner, d outer plus d inner. So I would get a value d outer plus d inner equals to 4 times d outer minus 4 times d inner. So I get a value of 3d outer equals to 5d inner. So d outer is 5 by 3 of d inner. And we got the value of that. We got the value of d outer. We got the value of d outer in terms of d inner. And similarly, you can take now the equation we got. The equation we got that we have two d's. One is that d. Next one is that d outer. So we got the beta value. Do we got the value of beta? I would say the value of beta would be equals to, beta comes out to be equals to d inner by d outer. That's 3 by 5. That's 0.6. So we got the value of beta. Let's write that beta value. So I would write 16t by pi d outer cube 1 by 1 minus 0.6 power 4. So we are only worried about now d outer. and the relation between d outer and d capital that d. So we have that equation. I would write that d mean equals to d, that is d outer plus d inner by 2. If I use that equation provided from the problem, I would use that equation now. I would write your d outer is 5 by 3. Let's write d inner equals to 3 by 5 of d outer. So I would write d outer plus 3 by 5 of d outer divided by 2, that is equals to d. So I got that. That means 5 plus 3, that's 8 by 5 d outer by 2, that's d. So I would write 0.8 of d outer equals to d. So your mean diameter, I would say mean diameter is 0.8 times your outer diameter. So you have this equation now. If you substitute the value of d, equals to 0.8 d naught, then I can get the relation. Now. Now if I write now the equation, I will write t solid by t hollow, that would be equals to this one. That would be equals to tau max pi by 16, and you have this d cube. The value of d cube I can substitute 0.8 d outer cube. You have this part, and similarly you can have other part also. So I can write the second part. Now we have this one, 16t upon pi d outer cube. 16t upon pi d outer cube. So I can write 16t upon pi d outer cube. 16t upon pi d. Yeah, this was in terms of tau. So I need to say the value of t hollow would be equals to that tau max times pi d outer cube 1 minus beta power 4 divided by 16. So I got this one now. Tau max, I would write tau max times pi d outer cube, and on the top I would write 16, and we have one more term, that's that 1 minus beta power 4. That's 1 minus beta power 4. 1 minus beta power 4. 1 minus beta power 4 0.6 value. So you got this value. You got this equation now. And you can solve that further. I would say, since your tau max is same, pi is same, d outer is same, 16 is same. So you got a value that 0.8 cube divided by 1 minus 0.6 power 4. You got this value now. That t solid by t hollow equals to 0.8 cube by 1 minus that 0.6 power 4. 0.8 cube divided by 1 minus 0.6 power 4. So you got this value of that's 10 by 17. You got the value of 10 by 17. So if I say that means your t hollow equals to 1.7 times t solid. So that means the torque transmitted, torque resisted, or we can say torque transmitted. Torque transmitted by hollow shaft. Is more 1.7 times that of solid section. So for the same shear stress and for the same weight, for the same value of tau max, so this is the condition that for the same tau max, for the same value of shear stress maximum and same area, or we can say same weight, your hollow section is best. I would say hollow section is best. You should prefer hollow section for torsion of shafts. In the torsion of shaft, you should prefer the material which is a hollow section. If you want to compare the two materials, that's one is your solid material, next one is your hollow material, but both have that same tau max and same weight. and you can prefer hollow section because it can transmit more amount of torque. So one more thing is that if you talk about stiffness, torsional stiffness, that is torsional rigidity upon length, that's GJ by L. We had the equation that T equals to TL by GJ, and from that you can write GJ by L, that is GJ by L equals to T by theta. Let's keep it for now because we have not got that value of theta. And next part is that get the value of theta now, the ratio of theta. Now we need to get the value of that ratio of theta. So you need to get this value of ratio of theta now. Angle of twist. Let's say that 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 we have to get the value of the torque ratio, that theta ratio. I would write theta equals to TL by GJ. Theta equals to TL by GJ. And then after that, I would write that theta hollow. If I write theta solid, that would be torque in the solid and length in the solid, then G for the solid and J for the solid. If the material is same, we have that G value is same, G is also same. And if we talk about that, that volume is same, or we can say that weight is same, that means gamma is also same because material is same. So I would write that means length is also same. Length is same, I would say. L is also same for the two materials. So that means I would write similarly for the hollow section, I would write T hollow, length hollow, and G hollow and J hollow. I would write L hollow equals to L solid equals to L, and G hollow equals to G solid equals to G. So I got these. If I use that, I would write T theta solid by theta hollow would be equals to T solid and J solid. And this one we have from this side, we have T hollow divided by J hollow. So I got this equation now. And I know the relation between T solid and T hollow. I would write T solid by T hollow, that was equals to 1 by 1.7. And the value of J hollow would be equals to pi by 32 d outer minus d outer 4 minus d inner 4, then divided by pi by 32 d power 4. So one more thing is that I know that is what we call as the ratio. I would say 1 by 1.7, and we got this value of d outer. Let's keep all those parameters in terms of d outer. So I would write 1 minus beta power 4 and divided by the value of d. We know that is 0.8 d outer. So you can write 0.8 power 4 d outer power 4. And you got that, and you can solve for that one. I would write 1 minus 0.6 power 4 and divided by 0.8 power 4. And you got this part, and divided by 1.7. That's 1.25. That's 1.25. You got a ratio of 1.25. So that means I would say that theta, the ratio was between theta solid and theta hollow. So I would write theta hollow equals to 0.8 of theta solid. That means the angle of twist formed, that angle of twist developed in hollow section is lesser. That of solid. For the same set of conditions, for the same shear stress maximum, for the same that weight, we got that hollow section is better than the other. So if I compare that, we wrote that equation earlier, that that ratio, that stiffness ratio. If I talk about that stiffness, let's say this is some stiffness ratio. That means there is some T by theta, and we already got that. If I write the stiffness of hollow by stiffness of solid, that's I write T of hollow by theta of hollow, and T of solid by theta of solid. If I write that, if I substitute that value also, I would say the theta value we got, that TH by TSY, we got that value of 1.7, and we got this value of theta solid by theta hollow, that is 1.25. And that means there is a value that 1.7, that's a very big value, 2.1250. That means the stiffness, we can say stiffness is more than twice. Stiffness of hollow section is more as compared to that of solid for the same set of conditions. So you can say your hollow section is best among the two. So let's take one more problem. Let's take one more problem now. Let's take one more problem. You have that shaft. After that you have same shaft. You have that same shaft, and one more shaft is there in the mid. That's the shaft, one more, and this is a hollow shaft. This is a hollow shaft. This is a hollow shaft. So the material is only this part, the dashed part. We have that material only. I would say the dimensions are that outer d outer. I would say that d outer is equals to 120 and d inner equals to 90. That means the thickness is equals to 15 millimeter. So one thing is that we don't know the value of d here, and same value of d is also here. D is also here. Now the moment the torque you are applying, the value of torque you are applying, that's here 6 kilonewton meter, and here 14, and here 26, and here also that 6 kilonewton meter. And the lengths of those shafts are equal to 0.9 meters, 0.7 meters, 0.5 meter. 579, 0.5, 0.9, 0.7, 0.5 meter. And let's say that A, B, C, D. This is your shaft configuration. Now the problem says for your hollow shaft, you need to say what is the value of maximum shear stress and what is the value of minimum shear stress in the hollow shaft. That's your BC shaft. In the BC shaft, get the value of maximum and minimum value of shear stress developed. We have this variation. This is some tau minimum and this is some tau maximum. You need to say this those values of tau max and tau minimum. And one more thing is that you need to get the value of diameter that's required diameter, d. The value of d, if the allowable shear stress in both the materials, that's AB and CD, that is equals to 65 megapascal. That means if the tau max allowable in those two shafts, that is equals to 65 megapascal. So this is second part of the problem. Let's go for the first part. For the tau max and tau minimum, you should have some value of torque. That we should have some torque on this section. You should have some value of torque. Let's say this is your shaft. And there should be some value of torque that should be applied on this one. And after that, you can write 16T upon pi d cube. Then I have that equation 1 minus beta power 4, and second one I have beta power 4 minus 1 minus beta power 4. I have these two equations I can write. So for that you have to get the values of those torques developed at all those sections. So we need to get the line diagram. We need to get the line diagram. I would say this is 6 and this is 14, and there is 26 and there is 6. If I make the TMD, can I make the TMD? If I want to make the TMD, I would say that there is an increase of 6. Then after that there is a decrease of by 14, such that the net value becomes equals to 8 minus 8. After that, now it increases. That 6 plus 14, that is 20. That is 20. And you have to subtract that 26. Then finally it becomes minus 6. After that, the equation becomes in this way. The diagram looks like this. So you have this 6, positive 6, 20, and you have this minus 6. So this is A, B, C, D. Now you can say that the torque developed in the part BC, that's your hollow shaft. There is a moment of there is a torque of 20 kilonewton meter. If I write that equation for the tau max and tau minimum for the hollow shaft, that's BC, that would be equals to 16 t upon pi d cube, pi d outer cube, pi d outer cube, pi d outer cube, and 1 minus beta power 4. Value of beta equals to 90 by 120, that's 0.75 power 4. If I solve this equation, I would get a value of 86.23 megapascal. Now if I want to solve that tau minimum in the BC, that's the equation we have 16 t upon pi d cube, but the d is d outer, d inner. You need to take d inner, that's 90 cube. So let's make it in a different color, that's 90 cube, and we have that equation of the factor of that beta power 4, 1 minus beta power 4, and you got this one, and you can get the value that is equals to 64.6725 megapascal. So if I plot the variation, let's say this is some circle. If I plot the variation, I would say, and there is a hollow section also. It's a hollow section. I would say this is there is a shear stress of that's equals to 86.23, and there is a minimum value of shear stress that is 64.6725. I would say there is a linear variation between the two. Similarly, from the other side, in this way. So I would say this is some shear stress variation for the hollow section. And in the other part that's hollow, there is no material, there is no stress. Stress is for material, because there is no stress here, no stress, because it is free. So you got this. Now you want to say for the second part of the problem that was saying you need to get the value of diameter, required diameter d, if the allowable shear stresses is equals to 65. Now you need to get the value of d here, and you need to get the value of d here. But based on that, if you analyze from the torque, TMD, both have the value of 6. Torque equals to 6 for both the spans. That's TAB equals to TCD, that is 6 kilonewton meter. And we have that condition given that both have that shear stress equals to allowable shear stress of 65. So that means the diameter for both those sections would be same. So that means diameter is same at the rate of tau max is also same. Because tau max is also same, that means for the same torque and same tau, you can have diameter same, because from the equation we have that tau equals to 16t upon pi d cube. From the equation, tau by r equals to 6 t by j. For the same value of tau max, for the same value of tau and t, we say that if I compare two, I would write that means for the two we have, let's say this is for the AB and this is for the CD. I would write same value of tau max by r equals to t max by j. So I would say this and this goes, this and this goes. So we are left with r and j. I would say RAB, JAB, RAB, JAB. It should be also same. Let's solve that. Let's solve for the first one of those. I would say that tau max is equals to 65 megapascal. I would say 65 megapascal is equals to 16. Torque value equals to 6 kilonewton meter. 6 10 to the power 6 Newton millimeter. So 6 kilonewton meter, pi d cube. That's millimeter cube. So I would say diameter equals to Diameter equals to 77.8. That is some value of answer from the calculator you get. Then do the 1/3 of that. 77.8 millimeter. 77.8 millimeter. 77. So this is 90. This one is 77.8. Let's take one more. Let's take one more problem. 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 So we have problem 15, I would say. There is a solid section, solid section, and diameter 150 millimeter, and you are applying a torque of 20 kilonewton meter, and also a bending moment that is positive sagging, let's say positive sagging bending moment of 12 kilonewton meter, and you are applying also axial thrust. Let's say that is tensile. I would assume that that's tensile, 200 kilonewton. So it's provided that you can assume that this is positive moment, this is some tensile force of 200. Now you got these three conditions of loading. Now one more thing that you need to get. So you need to get the value of major and minor principal stresses at extreme fibers of along vertical axis. That's A comma B. At A comma B, you need to say what is the stresses, major and minor principal stresses. Let's say this is vertical axis. I would say this is A and B. So you need to say what's the major and minor principal stresses on those 2 points. So we have 2 different stress elements. You need to say what is the different loading conditions, and you can get the sigma 1, sigma 2. Now you need to convert that those loadings. Because of those loadings, moments, and forces, you need to convert it into stresses, shear and normal. Then after that, you can get the that major minor principal stresses. Now if you assume that bending moment is positive, that sagging bending moment, that means that the bending stress variation would be in this way. Let's say this is negative, positive. I would say this is compressive, this is tensile. For this one, sagging bending moment, I would say this is my by I. That's 32 m by pi d cube. If you're talking about that extreme fiber, that means y should be equals to d by 2. That means you go to the equation, you get a value of 32 m by pi d cube. And similarly, if you are applying a torque, I would say there's some variation of that 16t upon pi d cube. Tau max equals to 16t upon pi d cube. That's tau max. Let's write it as tau t because of torsion. And third one is that axial thrust. So you're applying normal to the surface. You have normal to the surface. You're applying a load. So let's say this is some load of axial thrust to P equals to 200 kilonewton. So there's some stress developed normal to the surface. I would say that is normal stress. That means I would write it as sigma normal. That is equals to sigma normal or sigma axial. You can say. Let's call it as sigma axial. I would say that equals to P by A, area, load by area. That's P by A. That's P by pi d squared by 4. So you got this one. You got the 3 different stresses. Now you want to say you have this section. Now. Now one more thing is that you have the section. Okay, you got the section. There is some neutral axis. Let's say this is some ZZ axis. This is some ZZ axis. There is one YY axis also. Let's say this is YY axis. And there's out of the plane that's called as XX axis. X axis, I would say. That's XX axis. I would say this one. So if you are applying moment, the moment you are applying, that's in the Z direction. MZ. So moment you are applying in the Z direction. So that means you are applying some bending moment of M. That is sagging bending moment. That's M. And you are applying axial stresses. That means normal to the surface, normal to the section. So you are applying some load of P, normal to the section. Let's say this is some P axial force, and you are applying a torque of 20 kilonewton meter. That is in the along the polar axis. That's out of the plane. So you're applying torque let's say this is some torque. I would say this is some torque Tx. So based on these, I can get the values of stresses. I have those equations. I would solve those equations now. Let's solve that values. We have tau max because of torsion. I would write 16 T kilonewton meter upon pi d cube. The value of d diameter here is 150. So I write 150 cube, and you convert into standard units, and you get a value of that tau because of torsion, that is equals to 30.19 megapascal. And that is same for the both 2 points. That way, if you have tau A and tau B because of torsion, we have the same values here on the both sides, because tau is same on the both two extremes because they are on the surface. On every point on the surface, if you take any point on the surface, you have same value of shear stresses because of torsion. You have same values of shear stresses at any r. You have same values of shear stress. So next one is that bending stresses. Bending stresses, that is equal to 32 bending moment of 12 kilonewton meter upon pi d cube. So you get a value of that bending stress equals to 36.23 megapascal. Now, if you say that this is the variation, this is compressive, this is tensile, that means top fiber, that is point A was on the top and bottom B was on the bottom. I would say I would generalize that. I would say sigma A equals to negative, that's negative compressive, and sigma at bottom, that is tensile megapascal. The value of stress is same, but the direction, I would say this is tensile, this is positive, and this is compressive, this is negative. So you got these two. Now third one is that you need to get the axial stresses. See, the axial stress variation is in this way. Each fiber gets stressed to an amount of P by A. So this is P by A, axial stress P. So axial stress is P by A. That means your sigma A equals to sigma B. And if the stress is tensile, if the load is tensile force, I would say axial thrust was tensile. That means your stresses are also tensile. I would say that is positive tensile stresses. Then that means I would write sigma A equals to sigma B. That equals to load of, what is the load? That's 200 kilonewton. 200 kilonewton by pi by 4 d square, 150 square millimeter square. So you get a value of stresses equals to a positive value of that's 11.32 megapascal. 11.32 megapascal. Now you want to say based on this one, I would say because of we know that if you have that section beam, any beam or any section, you apply load, we have moments P, then we say that here is some net value of Fx on the section, there is some value of Fy. So these are horizontal forces. So these are horizontal forces. So that means the stresses are also that sigma x and sigma x. So that's normal. That's horizontal stresses, I would say, in the x direction, I would say. And similarly, you are applying load on this one. You are applying load in the long axis. That means the stress is developed in the you are applying load in the x direction. That means sigma is also in the x direction. So both are in the same direction. If the stresses are both in the same direction, then I can do summation. So you have this section. A and B. You have these 2 points. Now the stresses, because of those normal stresses, you have to add. So let's talk about the bending stresses. Bending stresses are also normal stresses. They are normal to the surface section of that. If you have that variation, that's normal to the surface. That is your cross section XX. Any section, it may be circular cross section, it might be rectangular. So those are in that is sigma x. That's sigma x equals to mz y by izz. So that's sigma x. Similarly, you have this cross section, you are applying stresses P, px equals to px by a equals to sigma x. So now you need to say whether it's positive or whether it's tensile, positive or negative. You need to see that one. So at point A, you have compressive 36.23 and you have tensile 11.32. and at B you have positive 36.323 and plus 11.32. So you have that net value of sigma A and sigma B. Sigma A and sigma B, that's final value of let's say that this was your A dash and this was your B dash. I would say sigma A and sigma B, that's equals to 24.9 minus times, that's compressive. And on the bottom I would say 47.54 tensile. So you got two different values of normal stresses. So these are your final normal stresses on the point A and B. And for the torsional value of stresses, do you have solved those values because of torsion? Yeah, we have solved that value. That was 30.19. So the value of tau A and tau B is also same, 30.19. If you talk about direct shear stresses, do you have direct shear stresses because of transverse loading? Do you have transverse loading? Do you have that transverse loading? Any P tangential to the surface? We don't have that. We have the load that's out of the plane. That's P perpendicular to that cross section. That's normal stresses, normal force, axial thrust. That's in this way. But there is no load on that's transverse. There is no load vertical. That's tangential to the surface. That should give you direct shear stresses of that V by A, or you can say that that we have equation 4 by 3 tau average, that we have maximum value of 1.5 tau average. That's we can say tau because of direct shear stresses, that is 0. That is 0. So final value, if you now plot those, if you have those elements now, if you have that element now, I would say this is some point A, there is some point A, there is some point B. I would say for the point A, I would write that stress element as in this way, that there is some sigma x, there is some sigma x of sigma A, and for the B we have some value of sigma B, and we have some shear stress of tau. We have some shear stress of tau because of torsion, and same value we have for the A also, tau because of torsion. So if you write a sigma A, that's compressive, that's actually compressive. So you can show that arrow also. If you keep that sigma A is in this direction, that means you write that sigma A only. If you write the values, then you have to show this is some value of compressive, that we have that value of compressive stress at A, that was minus 24.9. So then you have to show that minus 24.9, that this was your element A, then you have to show 24.9, and there's some shear stress of that we got as tau T, and for this one we have tensile stress of that sigma B. So for these two you can write that now you can take that at point A, you can calculate major and minor principal stresses. That the equation we have, that is equal to sigma x plus sigma y by 2 plus minus root sigma x minus sigma y by 2 whole square plus tau xy whole square. So we have that sigma x equals to minus 24.9 plus 0 by 2, then plus minus that root 24.9 divided by 2 whole square plus the value of shear stress we got because of torsion. I can write that tau T square, the torsion value we got, that was equals to 30.19. So I can write 30.19 whole square. So I got a value of sigma 1 and sigma 2 at point A, that equals to 20.21 minus 45.11. So if you had that Mohr circle, I would say there is some stress of minus 40.11, and there is some stress of 20.21. So I would write this is some sigma 1, this is some sigma 2. Then after that I would say there is some vertical and there is some horizontal. This is tau and this is sigma. Then that means this is origin. And if your plane are, if you represent those planes, you have that planes for A, you have that sigma was your compressive, some value of compressive, that was equals to 24.9, and you have some shear stress of 30.19. So if I have that planes, I would say this is some plane P and Q. Let's say this is on plane P, and this is some plane Q, P and Q. If I write that plane for the plane P, I would write there is some stress in this way and there is some stress in this way. So anti-clockwise tau. So anti-clockwise tau would be somewhere here, and sigma is also negative. That means on this side. So there is some variation. There is some plane P such that here the values are sigma x, sigma a comma tau, sigma a comma tau. That's both are negative. Both are negative. And second one is that on that there is no normal stress. On the plane Q there is no normal stress, and only there is clockwise shear stress positive. So there is some positive shear stress and there is normal stress of 0. So it's on the that pure axis line. That means there is no normal stress on this plane. This is some plane Q, and you join those two. You can join those two. And after that you can get a value of center here. See, this is your center, this is radius, and you can make the circle such that the values we got here. And for the point B, you can take for the point B now. For the point B, you have this point B. There's some normal stress, that is tensile stress of 47.54, and there's some shear stress. There's some shear stress of 30.19, and you can say this is some plane P and Q. There is some plane P and Q. This is some reference line, and there is some this is some vertical tau line. I would say for the plane P, you have that 30 anti-clockwise, either here or either here, and after that you have normal tensile positive. That means plane P is somewhere here. That's having values of normal stress of 47.54 comma 30.19, and this one is positive, this one is negative. And after that you have plane Q, on which there is no normal stress. Plane Q is only having shear stress clockwise positive, so I can have that 30.19. This is 30.19, 0 comma 30.19. This is plane Q, and I can join those two by a straight line. So then after that I can say this is some center, and there's some radius. This is some radius of C. There's some radius of CP, such that we would get a circle. In this fashion, such that sigma 1 and sigma 2, we can solve those values. Sigma 1 and sigma 2. Sigma 1 is C plus R, and sigma 2 is C minus R. So value of C equals to value of C we know that is C sigma x plus sigma y by 2. That's 30.19 plus 0 by 2. Then plus radius. Radius we know the equation for radius equals to tau max. That is 30.19 minus 0 by 2 whole square plus tau xy whole square. The value of tau we know the value of tau we know that's 30.19, and tau value is 47. That sigma is 47.54. 30.19. So you got this one, and you can get plus minus sigma 1 comma sigma 2. So finally your sigma 1 equals to 62.19 megapascal, and sigma 2 equals to minus 14.65 megapascal. So if you compare those 2 points A and B, you got point on the point A. On the point A, you got that major principal stress of 20 and minor principal stress of 45. And but on this side, you got major value 62 and 14. That means this is your major. Out of those two, this is your major one, major plane. I would say this point B point is having major stresses of sigma 1, and there's some sigma 2 also on two different perpendicular planes. We can also calculate the location of that principal plane from the point B. So I would say that tan 2 theta p equals to 2 tau x by sigma x minus sigma y. So I can get the value of principal plane. Then I would say this one is your sigma 1, and this one is your sigma 2. Then I would see what is the sign for the two. I would then calculate that also. So this is your principal plane. Then one more thing is that if you want to calculate that tau max, can you calculate tau max? What should be the value of tau max now? From the 2 points, if you see the bending stresses is maximum on those 2 points. There is no option any other point we have where the bending stress is maximum. So at sigma A and sigma B, they are the maximum bending stresses, normal stresses. They are the maximum. If we take any other point, there we have that sigma lesser. If the sigma is lesser, that means your major principal stress would be also lesser, based on this equation. I would say based on those 2 points, we have out of those infinite number of points on the surface, on this cross section, if you have infinite number of points on this cross section, you take 2 points A and B, and I would say on point B you have major principal stresses sigma 1 and sigma 2. That's 62.19, and second one is at 14.65 negative, and you would have this major principal stress of 62.19. So if I write that tau max, we know that tau max equals to sigma 1 minus sigma 2 divided by 2. That's sigma max at point B. Sigma 1 minus sigma 2 divided by 2. And I can calculate that also. Based on these 2 values, I could get a value of tau max equals to 38.4 megapascal. 38.4 megapascal. So let's take one more. So we have that concept of torsional strain energy. We have that torsional strain energy. We call it as torsional strain energy. So we have that strain energy 1 by 2 m theta. Similarly, you got that integral m squared dx by 2 ei. And similarly, if you have that for the that we call as for the torsion, we can have that u equals to integral 1 by 2 t squared dx by gj. Based on that fact, if you have that cantilever, you apply that torque T, you take some differential element dx at length of x, you would say there's some strain energy, small strain energy stored in that dx. I would say that equals to 1 by 2 some torque T into some small value of d theta contributed by that dx strip. I would say that d theta would be equals to that torque you applied on this cross section. If you have free body diagram, I would say there will be some T and there will be some G balancing. This will be clockwise, this is anti-clockwise, this is some anti-clockwise. So that's some T. So I would write T some small dx by gj, and we have one more T here, so I can get T square dx by 2 gj. And if you then integrate that total 0 to L, so you got this value, that strain energy stored in the because of torsion in the shaft, that's equals to T square dx by 2 gj. Now the thing is that we have the equation that torsion formula T by tau by R, T by J, G theta by L. We have this equation. Now you can do one thing. Now if you integrate it, let's integrate it. I would say this is T square, your T is constant. Let's say T is constant function T. And for the entire section we have TMD. So I would write T square and integral dx equals to L. 0 to L integral 0 to L dx, that is L. So TL by 2 gj, that's your strain energy. You got this equation 1. And you can take the now second one is that if you take torsion in terms of tau from this result, if you take tau in terms of torsion, if you take this tau in terms of tau, if you take this T in terms of tau, I would say tau, that's T equals to tau J by R. T equals to tau J by R. And I substitute here that value of tau, that value of T, sorry. So I would write 0 to L, the value of tau, that value of T equals to tau J by R. And you have that dx, you have that gj also, 2 gj. Now one thing is that if you take tau, the value of tau at any r is a function. We say tau at any r is a function of that r, because tau is varying with the r. If you have that solid section, solid circular shaft, I say that the shear stress variation is a linear function of r. So you take that shaft, there is some center O. You go from center O to some value of r, and you take some value of small that strip dr. You take some strip of dr. Because your tau is varying along the r, that means you have to take the strip at particular r, such that you would say what is the summation of those small strips that are contributing that variable tau, and I need to get the value of overall that strain energy contributed because of those infinite number of strips. I would say there is some strip of dr, thickness of dr strip. Then I would say because tau vary along r, so I need to take strip of dr. You take dr strip, you say what is the strain energy stored in that strip of dr strip. So you would get some strain energy, then you would integrate it from 0 to r, from 0 to capital R. Then you integrate it 0 to r. If you have this, do you know what's the volume of that strip? Can you tell me what's the volume of that strip? If you have this strip, for the entire length, there's some strip for the entire length. Can you tell me what's the area of that? I would say there is a strip whose area would be equals to 2 pi r and thickness of dr, and the length is L, so I would write volume equals to 2 pi r dr L. So this is your volume, 2 pi r dr into L. 2 pi r dr into L. 2 pi r dr into L. Yeah, one more thing is that, so you got this one. So we got that part. Now if you say your tau j by r, we know that variation tau max by r equals to tau by small r. So you can say the value of tau here would be, if you want to keep it as a constant function, then you have to keep it as a maximum value of tau max. If I say that in this way, I would say there is some value of tau max divided by r, and you multiply with that r. So you got this value of tau, and you have already that r is also there, and you have that dx, you have that 2gj. See, one more thing is that you can do it in this way. You can do it in this way. You have that strain energy is equals to half of stress into strain. Do you know this? If you talk about modulus of resilience equals to that strain area of that stress strain curve up to the elastic limit. Similarly, if you talk about that, this was your modulus of resonance, this was per unit volume. This is strain energy per unit volume. That is 1 by 2 sigma E. Similarly, on that way, if you take total strain energy because of torsion, that is 1 by 2 tau into phi or theta, tau into theta, and you would write the value of volume. You write this way. If you solve it this way, I would say value of tau, the value of theta, I know that value of theta from the equation that tau equals to g theta. I would say that value of 1 by 2 tau square g into volume. That's your strain energy. Tau square g by 2. Sorry. Tau square v by 2g. Tau square by tau theta. So this is the equation. I would write tau square v by 2g. So if I solve it, once we took that smaller differential element of dr strip, dr strip, and I said that volume equals to 2 pi r dr L, 2 pi r dr into L, if you have that length of L. So you take that, if you have that equation, I would say the small strain energy stored in that strip, of dr, that's equals to 1 by 2. There's some tau value of tau square and divided by g, and there is some volume of 2 pi r dr L. So this is your equation. Now you have this equation. Now the thing is that your tau is also a function of, tau itself is a function of r. It is a function of r, and if you want to take that tau at any r, and tau max at capital R, So if you have that, if you substitute that value of tau max for capital R and you multiply for small r, that it would give you a shear stress value such that it is a constant function and it is not varying with the radius r, because it is a fixed value now. I want to see what's the effect of that r now, only that r in the integral now. So that's, you have to square, then you are left with pi r dr L divided by g. So this is your strain energy stored in that strip of dr. So do you got it? Now? So this was the main part for the derivation. So you got this one. So if you take that overall strain energy stored in that entire shaft, I would say you integrate it from that small r to capital R, 0 to capital R, sorry. You have that strip at particular value of r. The value of r can be from 0 to, it can be up to that capital R. So you have that 0 to r, tau max. Actually, you have to square it, divided by r square. There is square, and there is one more, that is pi r square dr L by g. So you got this equation now. Now if you integrate it, I would say that is equals to 0 to r. Finally, you get a value of tau max square by r square g, and you have pi also, you have r power 4 by 4, you have L also here, so 0 to r. So you got this value. I would say that the value here comes out to be equals to tau max square pi L, and you have r square, capital R square, divided by g. So you got this value now. If I take that in terms of volume, I would say you have also 4 here. This 4 is also here. So you got a value of tau max square volume divided by 4g. So your strain energy stored in the shaft in terms of shear stress tau max, I would say that is equals to tau max square v divided by 4g. And same was in terms of, if you took in terms of torque, that was t square L by 2 gj. So if you have that strain energy because of axial force, that was equals to p square L by 2 ae. Similarly, you have t square L by 2 gj. Yeah, and for the that one, you have u equals to integral m square dx by 2 ei. Here we have u equals to integral t square dx by 2 gj, and you have one more, that 1 by 2 of p theta equals to strain energy. You have that u equals to 1 by 2 of m theta, small d theta. You write in terms of small d theta, and here we write small u strain energy equals to half of that t into d theta. And in terms of stress, if you write u equals to 1 by 2 of tau into volume, tau into that we call as that angle of twist theta, and you have some value of volume, and we use this equation for this derivation. So your tau was a function of r, and your theta was also a function of tau, and tau itself is a function of r. So you convert that tau into r. Using that equation of tau max by r, into small r. Then you integrate it from 0 to r. So let's have that. Similarly, if you want to derive, let's say you want to derive for the hollow section. If you want to derive that strain energy stored in the hollow section, that is equals to same equation we have, that in terms of tau max squared by 4g into volume. tau max square by 4g into volume, and you have to multiply one factor. That's 1 minus beta square, 1 plus beta square, 1 plus beta square, 1 plus beta square. So you have this. You have this now. If you want to take any problem, let's say that you have some shaft, and you are applying a torque of T at a location of, let's say this is L and this is also L. You want to make the different aspects of that problem. Let's say the line diagram looks like you are applying a clockwise moment about the polar axis. That means thumb points towards the fixed side. That's in this way, T. That means there should be some balancing T here. And if you want to make TMD, I would say there's some T in this way, there's some T downwards, such that the final TMD looks like this way, positive. If you want to make that section also, I would say there's some T acting on this one, T, there's some also T here, and if there is some T on this one, there should be someone to balance, but there is a free end, that means this is 0, that means this one is also 0. So this is the TMD. And if you want to say what is the maximum shear stresses, I would say tau max equals to that's 16 T upon pi d cubed. And if you want to say tau minimum, what is the shear stress in this part, I would say that is 0. Tau is 0 in this part A, B, C, that's tau BC equals to 0. And one more thing is, if you want to say what is the theta at the free end, let's say what is the theta at the free end, that is theta because of AB plus theta because of BC. Since for the theta BC we have no torque, that means no rotation contributed by that. That means that this is 0. Only the theta C is because of theta AB. So there's some rotation because of only torque developed in the part AB. That is TL by GJ. Now the thing is that if you have uniformly distributed torque, we can call it as uniformly distributed torque, UDT, uniformly distributed torque. So if the torque is there, we have the unit of torque equals to kilonewton meter. If you have that UDT, let's say there is some intensity of T, small t, I would say some torque T, small t, that is intensity having unit of kilonewton meter, but it is acting for per meter length. So this is the unit of that torque intensity, I would say. This is torque intensity also, we can say. Torque intensity. Now thing is that you have the shaft, and you are applying everywhere torque of T, small t. So there's some T acting kilonewton meter per meter. Let's say the total length is L, and you want to say what is the theta at the free end, and what is the torque developed at the fixed end. So I would say there's some, if you make that line diagram, I would say there's some smaller values of those values of smaller values of those. There is some smaller values of those T kilonewton meter per meter, such that if you make that TMD now, I would say that T at any x, if you cut any section, there's some torque developed T at any x, capital T at any x. I would say capital Tx at any x, that is equals to T into x, because this is your kilonewton meter per meter and you need for x meter, so such that final value of Tx kilonewton meter, and this is having a unit of kilonewton meter. So you got a value of that T at any x is a linear function of x, So if you talk about that, what should be the value of maximum torque? So that would be at the cantilever side, on this side, fixed side. So there's some maximum torque that can develop, that is equals to T into L, small t into L, that's capital T of capital torque T at the support A, that is T into L. So this is the TMD, I would say. This is the TMD. So there's some t at any x that we have t naught, or we can say small t into x. At any x, we have that linear variation. Now, if you want to say what's the theta, can you say what is the total theta we can have? Can you get the value of total theta? Now you can't directly say that theta equals TL by GJ, because at every strip, at every dx we have that along the length. I can say along the length, your torque is varying, t is varying. That means you have to take a small strip. You see what's the torque at that x, and you take the small dx strip of length L equals to dx, and then you see what is the theta contributed by that. You can do that way also, or you can do in this way, that strain energy, then you do Castigliano's theorem, dou u by dou torque, that is will be give you theta at any location, theta I. Do you get it? So now the thing is, if you talk about the strain energy at any x, because of this uniformly distributed torque, if you take that strain energy at any x, so what's the smaller strain energy stored by strip of dx at x from some free end, x from free end? If you want to take that strip of dx, let's take a strip of dx. If you take some strip of dx at some location of x, some strip of dx, you say what is the strain energy stored in that dx? I would say that small du is equals to some torque. We have that equation of 1 by 2 t d theta, 1 by 2 t d theta. I would write t at any x, and we have that small d theta, that is also function of tx, so that's also tx, and small dx by gj, dl by gj, that's your d theta. So I would write tx into tx dx by gj and 1 by 2. If I write it in this way, so I get a value of strain energy in that smaller strip. So if I say what is the total strain energy, that's integral 0 to u, that I would write u equals to integral 0 to L. If you go from 0 to L, I would write 1 by 2 t at any x square and dx by gj. And your t at any x, that is a function of your t at any x, that is a function of t into x. If I substitute that value t into x, that's 1 by 2 small t into smaller x whole square dx by gj, integral 0 to L. So that means we got a value of t square by 2, and we have that x square dx, that means x cubed by 3, 0 to L, and we have that 2g, we have that g also. So we got this equation. I would write that t square L cube by 12 g. Do we got this? We forgot some value g. We got this. We forgot this value of j. We forgot this j value j. So this is the equation. Is this the equation? T square L cube by 6 j. Do we forgot? Did we perform any mistake? Did we perform any mistake? Yeah. See, from this one, if you write that 1 by 2 dx square dx by gj, this 2 was already there too, so you don't have to add this twice. You don't have to have this twice, so you have to keep it twice. So final value would be 6 times. Final value of 6. So you got this total strain energy stored in the shaft. That's equal to g square L cubed by 6 gj. And now you want to say what is the theta at any location of I? Or if you say that theta at the free end, I would say calculate that dou u by dou t, that would be equals to t small t L cube by 3 gj, TL cube by 3 gj, yeah. It's strong. It's strong. If you had that, Castigliano's theorem, it says that if you apply a torque of T kilonewton meter, and you need to say what is the theta contributed here, what is the theta developed here, it says that theta at any free end, that means there should be some torque of T at the free end, there should be some torque of T at the free end, and there should be some torque of T at the free end. You say that the total strain energy developed in the structure divided by that torque at the free end. That means there should be some torque at the free end. But based on this one, we have only a UDL acting there, uniformly distributed torque. So there's some UDT. So there is no torque of T, that kilonewton meter. There's no torque here. We are having a intensity of T kilonewton meter per meter. So we need to do it in different way. If we need to get the value of T in the different way. So we got the total strain energy. Tx dx by Gj. If you write in this way, that the small strain, that the small theta contributed, we have that equation T equals to TL by Gj. If you say what is the small theta contributed by that small strip of dx, that I would write as T at any x, the strip you took at any x. We have the torque at that location Tx, and you took the strip of dx by Gj. If you use this equation, total theta, that means you have to integrate it 0 to L. If I use that value of Tx equals to Tx, and we have that dx by 2 Gj, by Gj, integral 0 to L. So I got a value of T, small value of T, L square by 2 Gj. So this is the theta at the free end. This is the total theta that is contributed by all those uniformly distributed torques for the entire length. This is the total theta contributed from 0 to L. Now this one I had solved the strain energy. Then I said that the theta at the free end would be in this way, but it's not correct. If you take that dou u by dou t, it's not that capital T, it's a small t. So that was a mistake here. That the small t is in the form of kilonewton per meter. So this is acting as a kilonewton, I would say. So we have to get the theta. For that theta, you need some moment, that's some t, capital T. So based on this fact, you should calculate in this way, that if you take small theta, that's contributed by because of that small strip at any x from the free end, and there is some UDT, and you take the strip, I would say there's some torque, net torque of T into x acting here, Tx. There's a length of dx. I would say that torque contributed by that strip is equals to that theta contributed by that strip d theta, that is some Tx into dx by Gj. Then you integrate it from 0 to L, T square, small t square L by 2 Gj. If we have that capital T, the equation we have that theta equals to T L by Gj, because your T is a function of that kilonewton meter per meter. So if you multiply length of L meter, so you would get a value of net torque of T, that's kilonewton meter. Then finally you would get a value of T L by Gj. But based on the integration we do, we got this value of 2 also. Now one more thing is that if you take that shaft such that the diameter is varying. So the diameter here is D2, here the diameter is D1, and you say what is the thing is that you need to get the value of theta at the free end. So you need to say what's the value of theta at the free end. Now because your D is varying, if you write that theta equals to T L by Gj, now you apply the torque of T. The value of torque is T. If you make the line diagram, I would say there's some T and there would be some balancing T. So the diagram of the TMD would be a constant value of TMD equals to T. So the T is fixed. T is a constant function. And length is also L. Now G is also fixed for the material. G is same. G is fixed. Now the j at any x, it's the function of that x, because diameter is varying, section is varying, that means your j is also varying. So if you go to add to a particular location of x from pre-end, and there you see what's the diameter here. I would say the diameter here is dx, such that dx, the diameter at any x, if you have that diameter at any x, I would say diameter at any x equals to d2 minus the variation of d2 minus d1 for length of L, and I need for length of x. So d2 minus some kx, d2 minus kx, d2 minus kx. So I got a value of diameter at any location of x, that's d2 minus kx, and the value of j at any x would be equals to pi by 32 and d at any x power 4. So because your d is varying, that means your j is varying, so your theta, you have to take that smaller theta, d theta. You have to take smaller d theta. So I would say, so your theta, if I take that smaller d theta contributed by smaller strip of, now if you take that smaller strip here, some smaller strip here, such that if I say that total theta contributed is equals to integral 0 to L, that T L by G J. So you take strip of dx, because you had that dx equals to T dx by G pi by 4 dx power. Actually this is small dx, and this one is the diameter at any x power 4. To make the confusions clear, let's say that this is some diameter capital dx. Let's say there is some diameter d at any x. So I would write capital D at any x, capital D at any x, capital D at any x. So this is some d at any x. I write that equation in terms of capital D at any x. I write dx power 4. So we got this theta contributed by smaller strip just after that smaller d diameter at any x. So this is your theta contributed by that strip. Now if you want to say what is the total theta, you had to take pi by 4 d to the power 4, pi by 4 and dx power 4. And you solve that now, you substitute the values. I would say 0 to L d by g pi 4. Is this 4 or this is 32? This is 32. This is 32 because we have polar moment of inertia. 32 t by pi g, and you have that dx also. You substitute the value of dx, that's 1 by d2 minus kx power 4, and you differentiate it, you integral it. So the equation becomes this one. So you can have that now. I will write 32 t upon pi g, and the integral will be, looks like, you have that equation that if you have this function of, let's say there's some function of ax, I would write ax power 4 dx integral, I would say that is equals to ax power minus 4 minus 1 plus 1 divided by minus 4 plus 1, and you have that internal differentiation d by dx of that ax. So that's your integration of that function. So I would say you have that 1 by 2 of d2 minus kx minus 4 plus 1, that's minus 3. Finally it becomes plus 3 downwards. Then you have that factor of minus 3, another factor of minus 3, and you have that internal differentiation of d2 minus kx. The internal differentiation would be equals to minus k and 0 to L. So this is your integration of this part. So I would get a value of 32 t by pi g, and you got a value of 3k. You got some value of 3 into k downwards, and you substitute the value of d2 minus kx in this way, that 1 by d2 minus d1 by L into x. Your value of x you have to keep as a function of L now for the first limit, upper limit. Similarly, minus lower limit. 1 by d2 minus d1 by L of x, and a value of x here was equals to 0. So you got this one now, whole cube. Then you have that. You have this equation now. This is your cube. So I would say this part goes 0. So we are left with that 32 t by 3 pi gk. Then we have that See, that becomes equals to d2 minus d2, that is 0, and you're left with positive d1 cube. So 1 by positive d1 cube minus 1 by positive d2 cube, positive d2 cube. So we got this equation now. And if you substitute the value of k also, I would write 32t by 3 pi g. Value of k was equals to d2 minus d1 by L, and you have this value of d2 cube minus d1 cube divided by d1 cube and d2 cube. So you got the final equation in terms of this one. So this is your theta. This is your theta total. The equation becomes theta equals to 32 d by 3 pi g d2 minus d1 by L d2 cube minus d1 cube by d1 cube d2 cube. Now let's have the one problem on this condition. Let's say that you have that varying shaft, diameter is varying. So let's say this is the diameter d, and the diameter here is 1.2 times of diameter d. So let's say this is diameter d1 and this is diameter d2, and you are applying a torque. Let's say you are applying a torque of t. You are applying a torque of t, length is L. So you need to say what is the theta. What is the theta total? What is the theta? Now you have those values of d and d2, and you can get the value of theta. So I would say I took that strip of dx at any location of at a location of x from capital D2. So then after that I have the equation d2 equals to d at any x equals to d2 minus d1 by L into dx into x. So I already have that equation. I already have that equation. If I use that equation now for this problem, so your d2 is equals to 1.2 d and your small d1 equals to d. If I use those values now, I would say your d2 equals to 1.2 d, and this one is your d, and similarly your d2 cube would be equals to 1.2 d whole cube, and this part equals to d cube. And after that, if you take d1 cube, that is equals to d cube, and this d2 cube equals to 1.2 d whole cube, and you solve it, and you get a value. You would get a value of that theta equals to 22.4691 TL by pi g d to the power 4. So we know that theta equation we have theta equals to TL by gj. If you take j in terms of pi by 32 d to the power 4 in this way, then the value comes out to be equals to 0.702 TL by gj, where your j value is equals to this one in terms of that small d. So either you can have this value or you can have this value. Now one more thing is there in the problem. It's saying that if you took the diameter as a varying function, so then after that you took d at any x. Now it's saying that the problem says that now you don't take the differential element. You directly take the average mean diameter. You take the mean diameter as calculation for the calculation. If you take the mean diameter for the calculations for the theta, if you take the mean diameter for the theta, you need to calculate the error that gets developed. Calculate the error based on the mean diameter, based on mean diameter of shaft. So if you say what is the mean diameter, you are having a d and you are having 1.2 d such that, so d mean would be equals to 1.2 d plus d divided by 2. That is 1.1 d. Isn't it 1.1 d? Yeah. Now if I use that equation directly, I'm assuming that there is a net constant value of that cross section. That's a diameter is fixed now, that's 1.1 d, and I know that equation that theta equals to TL by gj. The value of j is pi by 32 and d to the power 4. So if I use that value of j, the initial value of j, we have j was equals to pi by 4, pi by 32 d to the power 4. If I use in that format, so I would get a value of 0.683 TL by Gj. So I got this value of 0.683 times TL by Gj. And initially I got, based on the actual method based on the integration, I had 0.702. That means theta actual is more. Theta actual is more. So theta actual is more. So it's a conservative value that theta twisting would be more. So you have to be very cautious there. And based on the theta based on the mean diameter, it's saying that your theta would get developed that would be lesser. So it's that it's overestimating the strength of the material. So it might fail and you don't know. So you need to say what is the error now. What is the percentage error? So percentage error in the theta calculation would be equals to theta final minus theta initial by theta initial into 100. So I would say final theta was equals to 0.683, 0.683, 0.683 minus initial value of 0.702, 0.702 divided by initial value of 0.702 into 100. So a percentage decrease, I would say at 2.706 percentage. So this percent of amount of theta, there is an error of this percentage of theta based on that mean diameter. So let's say one more. Let's take one more. Let's take one more. So there's some problem, there is a problem, there is a problem, there is a problem. There's some problem that this is your 4 meter and normally horizontally projecting, that's one more beam we have. You're applying a torque, you're applying a transverse load of 20 kilonewton. So the spans are 4 meter and this one is also 4 meter, and this is your fixer side ABC. You need to say SFD, BMD, TMD. SFD, BMD, TMD, you need to draw those three. SFD, BMD, TMD. And see, this plane, this BC is, so you are looking from the horizontal view. So this is from the top view, if you say. This is top view. So you are looking from the top view at an angle of theta. So this angle here is 90 degrees. This is 90 degrees. This is 90. So this is normally projecting, horizontal beam normally projecting, but in the Z direction. So this is X, this is Y, and this is Z. So if you take the free body diagram of this one, so let's rotate it, or you can it's easier if you have this one. So it's a beam. You're applying a load of 20 for the length of 4. There will be some reaction of 20 upwards, a shear force of 20 upwards, and there will be a moment of 20 into 4, 80 kilonewton meter moment developed. So you got this part. There is no torsion for this part, and you can directly draw the SFD BMD for this one. I would say there is some line. You go. You have to take. You can go from the side. You can draw that. There is a 20 downwards. There is a 20 downwards. Thereafter, after that you have that upwards 20. So your SFD is your minus 20. So you got SFD of minus 20. SFD 20 kilonewton. Now after that, if you want to take BMD value, I would say there is some value of BMD that's in this way. This is your BMD. This is some BMD of that 80. So if you are looking from this side, so there is some BMD. There's a clockwise BMD moment developed. So I would say this is a positive BMD, positive. So from this side, I would say this is some positive BMD. I would say this is some sagging. Actually it is a hogging bending moment because it's not sagging. So because your moment is in this way, that you have this moment applied, and from the side you are applying a moment. So this is your negative. So as per sign conventions, this moment is negative. So there's some hogging bending moment of 80. This is hogging negative 80. Then it's a linear variation of that px, because moment at any x. If you got moment p at any x, I would say you had this one. So if you have this load, you cut at any section, I would say this is some function of x. I would say here the moments developed would be mx equals to minus times px. or px. So it's a function linear variation, that px. So you got the BMD and that SFD. If you draw TMD, TMD is like as 0, 0, 0. So this is your TMD, 0 function. Because there is no torque, there is no more TMD. Now for the second case, that same though, the internal forces would get transferred here. These two would get transferred for the AB. So let's have that AB now. Let's take that AB. I say that this is some AB, there's some AB, this is some AB, AB, and these reactions would get transferred. There's a 20 upwards. That means in this part there would be a 20 downwards. There would be a 20 downwards. And you have a moment of 80 that's clockwise. That's clockwise developed. That's clockwise. That's clockwise. That means on the other side there would be that would be anti-clockwise. So if you have that anti-clockwise, there is anti-clockwise moment. So such that this moment is along the polar axis. So this moment looks like in this fashion. It looks like in this fashion. So it's like a, yeah, it's like in this way. So anti-clockwise moment. If you have that anti-clockwise torque, so you rotate your right hand anti-clockwise such that thumb points towards the away from the section. So it's your line diagram would look like in this way, that you have that TMD of the value was equals to 80 kilonewton meter. So this is your T equals to 80 kilonewton meter, and a reaction of 80 kilonewton, and there would be some reaction of 80 in the side also, opposite side 80. That means the moment developed at A would be clockwise 80. And you can make the TMD now. Can you make the TMD? I would say this is some TMD, negative TMD, because your traverse is in this direction, but your arrows are in the opposite direction. So the sign convention for the torsion, we have that if the torsion is towards the section, you have this section. If the torsion is towards the section, that is positive TMD. That means the torsion is positive. And if the arrows are away from the section, that means they point away from the section, that is negative torsion. Torsion is negative. Similarly, you have that arrows away from the section, that is negative torsion. So you got the values of TMD. Now you need to say what is the BMD and what is the SFD. So now you can say there is some load of downwards 20, and there would be upward reaction of 20. So the SFD is your 20 constant, and this is your SFD for the part AB. And if you want to take BMD, you are applying load of 20. There would be some linear function of moment, that's 20 into 4, that's 80, negative hogging. So this is your BMD. Now let's take one more. Let's take one more problem. That now one more problem in the same way we have that in that same way we have that cantilever. Then after that we have normally projecting. We have same sort of normally projecting. This is also normally projecting, but it is in the horizontal. So this is your, let's say this is your Y, this is X, and this is Z. Yeah, Y is upwards. So you're looking from the top. So this is your top view. The previous problem was designed in this way, that you can easily get that. So your Y was in upwards. This was your Z direction, and this was your X direction. But in this one, you're viewing it in a way such that if you rotate it, I think no, you won't get that. So this problem is like, it's saying that you are looking now at this point. Initially you are looking somewhere here. You are looking here somewhere. So you are getting every three different perspectives. So you're seeing this is Y, this is X, and this is Z along out of the plane. But in this way, you are looking now here. You are looking here. So you are getting that this is your Z. Upwards you have to say this is X, Y. Upwards Y. You have to go upwards, then you say this is Y. And in your line, this is your Z and this is X. So let's have that problem now. Let's take the problem now. This is this, and this is this, and you're applying a load, and I show it in the form of cross. You're applying a load here, and you're applying a load here. So a load of 10 kilonewton and a load of 10 kilonewton. So this is top view. This is top view, and you are viewing from the top. That this cross means the arrow is downwards. The arrow is downwards. That means loading is downwards 10 kilonewton. Loading is downwards, and this one is also same, that 10 kilonewton downwards. That cross means it's downwards. It's downwards. Now you have this 4 meter, you have this 2 meter, and the name is equals to ABC. I can name them ABC. So you have to get SFD, BMD, TMD, SFD, BMD, TMD, SFD, BMD, TMD. Now, to get the clear picture of this part BC, you can't directly get this one, how this moments would get developed from this cross. So if you rotate it, so you can't get the clear picture of what's happening inside. So if I make that, if I rotate this BC, if I rotate it in this way, rotate it, let me rotate it anti-clockwise 90 degrees. So I would get a BC in this fashion. Now I can see what's happening. I know the loads are acting downwards. You cut just before right of B, so the effect of that 10 won't be there. So there is some load, there's some downward load at C, that is 10 kilonewton. So I would say there would be reactions developed here. The shear force would be 10, and the bending moment value would be equals to 20. This is your M developed at B, that is 20 kilonewton meter. That's 20 kilonewton meter. Now I can say the SFD would look like in this way, positive 10, and the BMD would look like negative linear variation 20, negative hogging. So if I rotate those diagrams now, I can say now the BMD and SFD would look like. So this was your BC. I would say this is your SFD, positive 10, and this is your bending moment diagram. That's linearly varying. So this is your negative hogging. You can say this is your hogging. This is your negative, how much? 20 kilonewton meter BMD. And your TMD is a straight line. That is a TMD. That's a zero line. TMD is a zero line. Now for the AB, those internal forces and internal reactions would get transferred. This is your AB for a length of 4 meter, and for this part you had that 10 kilonewton upwards. That means for this one it would be downwards 10. It would be 10, and there was a moment of anti-clockwise moment of 10, 20, anti-clockwise 20, and on the other part there would be clockwise 20. So there would be clockwise 20. Now this was moment for this one. This was for moment for BC, but it would be moment for this would be moment for that. This would be torque for AB, because it is acting on this line. So I can have that this moment. I can show it now in this way, that if this is clockwise, that means I have to make it in this way, that the arrow is in this way, such that it's going in this way, 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 in this way. So this is your direction of arrow. Now direction of arrow is clockwise. That means that is in this way. That's anti-clockwise about the polar axis. Anti-clockwise about the polar axis. Anti-clockwise about the polar axis. So this way, this is clockwise. You get based on the moment diagram. You have to show it on the polar axis now. This is polar axis. This is clockwise moment, and you want to say what's the direction of arrow. So this looks like, if I make it in this way, I would say it's rotating in this way. It's rotating clockwise. So I can show this is clockwise. I can show this is clockwise moment. Can I show this it in this way, that is a clockwise moment? It's a clockwise moment, or something else, If I say This is clockwise moment. That means it's acting in this way. No, if this is, yeah, I got it. See, I got it. Now the thing is that if this is clockwise 20, that means let's say that there is some moment, there is some torsion. If I say that there's torsion of clockwise about this polar axis, that means it is rotating in this way. It's rotating in this way about this. So, but actually your torque is clockwise. Actually, your moment is clockwise 20, so that gets transferred as a torque. Always gets confused for this part. See. If this is the direction, if this is the direction of torsion, your torque is, your moment is actually in this way 20. So this is having a direction of anti-clockwise, but your moment is clockwise. That means the direction should be in this way. Yeah, direction should be in this way. If you have this moment now, I would say you had that torque of clockwise. This is your clockwise torque. So finally, I would say the direction of that torque would be that in the form of clockwise. I would say in the form of clockwise. This is in the form of clockwise. It was very easy. If I see directly, you have to make from this clockwise arrow. You have to make the clockwise arrow for the torque. This way. Now, if you make it in this way, you have to make the clockwise arrow. How can you make the clockwise arrow? This is your clockwise arrow. If you want to make in this way, this one is your clockwise arrow. If you want to make it in this way, this is your clockwise arrow. Isn't it? Is this clockwise arrow? Yeah. Based on this fact, I get confused. When I draw sometimes in this way, I get confused. So you should make it clockwise. That if this is arrow, the clockwise should be in this way. I think this is not clockwise. This is anti-clockwise. So you have to make it clockwise. Yeah, in this way. Finally we got this part. Which where we got clockwise. This one. So we have to keep this sign now. So we have this moment of that's actually on this polar axis now. This is your right hand. You have to rotate it anti-clockwise because you can't have that rotation in this way clockwise. Now on the polar axis it's anti-clockwise using the right hand thumb rule. So this is anti-clockwise for the right hand. So this looks like T 20 kilonewton meter. So if you use this now, I would say this is your line diagram 20 in this way. Yeah, 20, and there would be some reaction 20 in this way. That means here the direction would be opposite. That is clockwise moment of 20. This is 20, and here the moment was in this way 20. Let's have that at TMD now. I would say in the direction opposite to that, let's say this was your reference line, and that means you have to go downwards 20 because your arrows are out of the cross section, pointing away from the cross section. So you have negative TMD of 20 for the part AB. And if you want to make SFT BMD, that's easier. And one more load that was there that I missed. So that is for the BMD calculations. So from the problem we had two loads. One is your at the C, next one is at the B. Now you have to encounter that point B also, the load at B also. So there is some load also at B. I would say there is some vertical load also at B. That's 10 kilonewton. Now you are looking for this part in your side view, And this was your top view. This, you're looking from the top view, that vertical load is, some vertical load is going downwards, and but you're looking from the top, so you're looking some, you're getting some cross here. So if, but you're now you're initially you are looking from the top, now you're looking from the side, that this is your side beam of depth D, and you are looking that vertical load is downwards equals to 20, that 10 kilonewton, and we had already that reaction of 10 also, and we had the torsion of 20. Now you got a net value of 20 kilonewton. You got a net value of 20 kilonewton downwards, and for that you have to calculate the TMD and SFD. Yeah, SFD and BMD. So net value of 20, you have this 4 meter, so I can say SFD is 20 positive, BMD is negative, hogging 20 into 480, linear variation, BMD SFD. So this there is only one confusion I had, that's this arrows. I get confused for these arrows. Next we have, let's take next problem, that is, I would call it as problem 12. I would say you had some shaft, cylindrical shaft of steel. So your tensile stresses, I would say yield strength, tensile yield strength of this specimen is equal to 550 megapascal, and you're applying static loads, because we are dealing with the statics, so you are applying static loads such that they deliver you a bending moment of 700 kilonewton millimeter and torsional moment of 400 kilonewton millimeter. And is there any yeah, you have two different loads, bending moment and torsional moment. And one more thing is that there's no mention of that diameter, so you don't know the diameter. You need to say what is the diameter D for the set of conditions that your value of E equals to 200 gigapascal and Poisson ratio 0.25. And you're saying that you have to use maximum shear stress theory for the design of diameter D. To get the diameter D, you have to use maximum shear stress theory, and you have to use also factor of safety corresponding to that equals to 1.5. So you have to use the maximum shear stress theory. So based on these values, you have to get finally the diameter D. So if I say that your tau max, as per maximum shear stress theory says that your tau max should be lesser or equals to that tau max in the uniaxial. This is tau max in the general loading. That's for the 3D case. Tau max for the general, tau max for the multi-axial loading. Multi-axial loading should be lesser than or equal to tau max for the that's tau max for the uniaxial loading. For the uniaxial loading, you apply load of P, that is gives you sigma x. So finally you say tau max equals to sigma by 2. So that's your sigma y by 2. Here we have yield strength in the uniaxial testing. So your tau max should be less than or equal to sigma y by 2 factor of safety. Now one more thing is that how can you get the sigma max? So you are provided with those moments and those torsion moments, bending moment and torsion moment. So from this you can get sigma and you can get tau. So there is some element having tau and there's some element having sigma also on one of the planes. So I can say there is some sigma squared by 2 minus 0 whole square plus tau xy whole square. This is some radius of r such that this is your tau max. Can I get those values now? Based on these values, if I say your bending moment, your sigma, because of bending moment, that is equals to my by I, such that is equals to 32m by pi d cube. Do you know this equation? 32m by pi d cube. Similarly, your sigma tau, because of your shear stress is developed because of torsion, that is equals to 16t by pi d cube. Yeah, we have unknown of d cube, so we have unknown of that d. We know values of those. We have that equation. If I use that equation now, I would say that the tau max, that is equals to that under root 32m by pi d cube plus 16t by pi d cube, and that should be less than or equal to that sigma y by 2 factor of safety, sigma y by 2 into factor of safety. So if I use those values, I would say 32, the value of m was equals to 700 kilonewton millimeter. So I would write 700 into 10 to the power 5 Newton millimeter, and similarly divided by pi d cube. Pi, I don't know the value of that d cube, so let's keep it as pi d cube, and it's common for both the terms. So I would keep them common. Then after that plus 16t by pi d cube, 16t by pi d cube, 16t Newton millimeter by pi d cube. So this value, and that should be less than or equal to, I would say that should be less than or equal to your sigma yield, that's yield strength in tensile testing, that is 550 megapascal. So that is 550 Newton per mm square. Sigma y by 2 into factor of safety was 1.5. You square it. So finally, then after that, you solve it further, and you would get a value of t equals to answer, then inverse, then finally you get a diameter comes out to be equals to 28.19 millimeter. So let's take one more. Let's call it as a problem 4. Let's have that problem 4. I would say that problem says we have two different solid shafts. One is having diameter of d, and next one is having diameter of one is having d1 and next one is having d2. Now the thing is that two different solid shafts. Now they have to transmit same amount of power. They transmit same amount of power individually. Transmit how much power? 200 horsepower. That's metric horsepower. 200 metric horsepower they have to transmit each. Both have to transmit same amount of torque. That means torque developed will be same. Let's say that torque, the torque here is T1 and their torque for this one is T2. They have to transmit same amount of power. They have to transmit same amount at different omega, at omega 1 and omega 2, So it's rotating with omega 1, it's rotating with a rotational speed of omega 2. So that omega 1 equals to 2 pi nu, and this one is also 2 pi nu. This is nu 1, nu 2. That's 2 pi n1 by 60, and this is 2 pi n2 by 60. Now the problem says that the first shaft, that shaft 1, that's having those RPM of that's operating at, so your shaft 1 at this one operates at that 20 RPM, and second one operates at 20,000 RPM. So your N1 and N2 is different. That means omega 1 and omega 2 is different. So yeah, we have different omega, but the power is same. We have the equation power equals to T times omega. So that means your power is a function that's constant. That means T1 omega 1 equals to T2 omega 2. So your torque 1 would be different as compared to torque 2, because your omega 1 is different as compared to omega 2. So we got this equation. Now, so you got this problem, and it's saying that material is same, material is also same, and that means tau max is same for the two materials. That is 700 kg per centimeter square. This is tau max. Maximum stresses per centimeter square area is equals to 700 kgs. So 700 kgs per centimeter square. Now we want to say you need to get different torques. If you get the different torques, then after that you can get the diameters. You don't know the value of diameter, but you have this condition, and you have also given that total power, how much you have to transmit, and you also know omega, and you can get the power 1 and you can get the torque 1 and torque 2. Based on that, you can use the equation that tau max 16t by pi d cube, and you can get the diameter of those. So you need to get diameter 1, diameter 2. You need to get these two. So for that, you use the equation first one, that is power transmission equation. So you write for the case one. So your case one, your shaft one, I would write shaft one. That says that total power equals to total power of 200 horsepower, 200 horsepower metric, 200 metric horsepower, 200 metric horsepower, I would write MHP, and that equals to torque 1 into omega 1, 20 rpm. So that's equals to 2 pi nt t1. So your omega 1 is equals to, I would say, n1 equals to 620 rpm. So you got this equation. So I can get the value of torque 1. That's, I would write as this, the unit here would be equals to seconds, and here I would convert that into Newton meters per second. I would say your 1 metric horsepower equals to 735.5 watts. That equals to Newton meter per second. So I can get the value of torque 1. That's I would write as, let's write equation is in the terms of that 200 into 735.5 Newton meter per second, and you have this 2 pi 20 by 60. You have the second also 60 seconds, that is torque 1. So you got a value of torque 1 equals to 70235.08 Newton meter. And for the shaft 2, you can similarly write for the shaft 2, so you can write that power of 200 megahertz power, metric horsepower, 735.5 Newton meter per second. That equals to 2 pi n2, that was 20,000 rpm. 2 pi n2 by 60, so finally seconds. So I would write torque T2. So your torque T2 develops equals to 70.235 Newton meter. So you got the torque 1 and torque 2. Now, if you need the diameter 1 and diameter 2, you have that shear stress equals to 700 kg per centimeter square. So you can write that tau max equals to, you're right, that tau max equals to 16t upon pi d 1 cube. Can I write in this way? Your tau max is same for the two materials. So that is equals to some value of 700 kgs. So 700 kgs, I can write 700 kgs per centimeter square. I would write 10 power minus 4 meters square. So you got this stress, and if you multiply that g also, if you multiply that g, you get it in terms of Newton. So I would write 9.81 meter per second square, such that it becomes in terms of Newton per meter square. So I would write that equals to 16. Torque 1 is equal to 70235.08 Newton meter divided by pi d1 cube. So you can get a value of diameter 1 in terms of some meter cube, some answer in meters. So finally you would get a value of diameter 1 equals to 172.6 millimeter. So you got this diameter 1. And for the second case, you got the torque. I would write tau max, that equals to 16t2 by pi d2 cube. That equals to some 700 kgs per centimeter square into some g also 9.81. So that equals to 16t2. That is 16 into t2, 70.235 Newton meter divided by pi d2 cube. So you got a value of d2 equals to, that d2 equals to 17.26 millimeter. So now you have to comment on the problem, says that you have to comment on the savings of the materials. Comment on the savings, material savings. So for the same material was same because your G was same, your tau max was same, but you use one with diameter D1 and next one with diameter D2, and there was some omega 1, there was some omega 2. The power, you have to transmit same amount of power, There's no other option. Power is same. So there would be some torque 1 developed for this one, and there would be some torque 2 developed for this one, such that the torques should be lesser than the torques effective would be such that the tau should be less than tau max. So that's also satisfied. Now you want to say, based on these two options of omega 1 and omega 2, based on different omega rotational speeds, what's the diameter 1 and diameter 2? You need to compare those two, and after that you need to say what is the savings of the material. So you have, let's say you are having some motor, here. This was your motor, and the length was fixed at L equals to, let's say 10 meter, let's say 2 meter. Length was fixed between 2. Here was some gear, there was some gear that was rotating, so there was some gear. Now length is fixed. Now you either you use diameter D1 or you use diameter D2. Then the one is rotating with omega 1, second one is rotating with omega 2. Both are having the same material, having same stress, shear stress maximum, that is 700 kgs per centimeter square. And you want to say what's the difference in the material savings. You need to compare that, because your length is same, gamma is same, that means your volume is varying. Because gamma is same, L is same, only your volume is varying. That is because your diameter is varying. So if you take cross section, pi by 4 d square, d1 square, pi by 4 d2 square. So if you see on the material savings, we say how much volume is saved. Because length is fixed, that means your area, how much area is saved. You need to say how much area is saved. So that is a function of d square. That is a function of d square. Now if I say that is a function of d square, so I got the diameter 1 and diameter 2. So if you analyze those two diameters, if I had that diameter 1 and diameter 2, so if I had that, so this is your diameter 1, this is your diameter 2. Diameter 1, diameter 2. If I write material saving for the same gamma is same, L is same, that means material saving is a function of volume. So volume equals to A into L. So how much area is saved? So if I write area 1 by area 2, that's a function of pi by 4 d square, pi by 4 d square. So I would write d1 square by d2 square. So your area is a function of d square. So I write that area 1 would be equals to 172.6 whole square divided by diameter 2 was 17.26 whole square. So I got a value of, that's 100. I got a value of 100. That means that area 2 is 1 by 100th of area 1. Can I say that? That means if the omega for the material 2, your omega was 20,000 rpm. Your number of revolutions per minute was equals to 20,000 or 20,000 rpm. And in this first case, you are having a omega of 20 rpm. So you had two different omegas, and the one having more omega for the same amount of power, you need lesser area, you need lesser quantity of material, you need lesser material. If you want to rotate it with maximum speed, maximum rotational speed, that means you need lesser amount of area. That means material would be saved by a huge amount. So your area is saved 100 times, I would say. Saved 99 times. 99 times, I would say. Saving is 99, but area 1, that means area 2 is only 100th of area 1. So let's say that there is one more equation we got. If I have that equation, if you analyze those equations, I have that 16t by pi d cube, that is tau. So, and area is a function of d square. So the savings, I would say, savings is a function of d square. So I would say d square equals to from the torque equation. If I write the torque equals to power by n, number of rotations, because we have 2 pi n t by 60 equals to power. So if I write torque is a function of p by n. So torque is a function of P by N. So if you substitute in terms of torque, you have P by N, then we can say your diameter and diameter. So your equation becomes 16T by some function of pi, some constants we have that. Then we have 3 that d cube, and we have some n. So that's some value of tau. So let's say there's some tau. So I got an equation that d cube equals to 1 by n. And if I say that d square would be equals to 1 by third of, and I would do it in this way. Can I do it in this way? So your area 2 is a function of, or diameter square, or area savings, I would say area is a function of n 2 by 3. If I substitute these values also in this way also, I can solve. I would say saving ratio, I would say that is n inverse of n. So initially the n was equals to 20, 2 by 3. In the first case, in the second case, that 20, it was 2000, 20,000, 2 by 3. Then that's also 100. That's also 100. Let's say that we have one more problem, we have that specimen of steel. You have steel specimen of gauge length, L gauge length equals to 150 mm. You apply tensile force of 10 kilonewton, and the length was 150, and the deformation extension, I would say elongation of that that length, initial length, would be equals to 6.3110 to the power minus 2 millimeter. So diameter here is 12 mm diameter, phi. Diameter of the bar is 12 mm. And same bar, same material, same you are taking for the torsion test. So you are applying torque clockwise, anti-clockwise. Let's say you are applying a torque of T equals to 10 Newton meter. And the theta is same, diameter is same. Yeah, diameter is same. Length is also same, 150 millimeter. And you got a value of theta equals to 0.5. Angle of twist, angle of torque, angle of twist, torsional deflection. So you got this part now. And you want to say you need to get those elastic constants. E, G, K, mu. These values you need to solve for. You need to solve for those values of E, G, K, mu. Now, if I write that equation, first equation, that delta equals to PL by AE, and I can get the value of E. So I would write delta value of 6.3110 to the power minus 2 millimeter. That equals to some load of P, 10 kilonewton, length of 150 millimeter, area of pi by 4, 12 square millimeter square, and value of E. So I got a value of E equals to 210 gigapascal. That is 2.110 to the power 5 Newton per millimeter square. That's 210 into 10 to the power 3 megapascal. So we got this one. Similarly, from the second part, we have theta equals to TL by GJ. Angle of twist is a function of length into T by GJ. So if I write that, I would say 0.5. I have to keep it in terms of radians. So I would say 0.5 degrees by 180 degrees into pi. That is equals to T 10 into 10 to the power 6 Newton millimeter. TL by GJ, length of 150 millimeter, by G, and value of J, polar moment of inertia, that is pi by 32, diameter power 4, pi by 32, diameter power 4. The diameter was your 12 millimeter power 4, 12 power 4. So I got a value of G comes to be equals to 84.4 gigapascal. I would say 84.4 10 to the power 3 megapascal. So you got this one. Now from the equation we have E equals to 2g 1 plus mu. I can get the value of mu equals to E by 2g minus 1. So if I use those values, I would say 210 by 84.4 minus 1, that is 2 times. So I can get a value of mu equals to, mu comes out to be equals to 0.2441. So if I get the value of mu, I have one more equation that E equals to 3k 1 minus 2 mu. So I can get a value of k equals to E by 3 1 minus 2 mu. Is this the way? E by 3. So I have that value of E I got as 210 gigapascals divided by 3, 1 minus 2 into mu. Value of mu was 0.2441. So you got a value of E. You got a value of that K equals to 1.37 10 to the power 5 megapascal. So let's take one more problem. Let's take the, that is the final problem for this lecture. That is the final problem for this lecture. You have this, let's call it as a problem 18. You have a torque, you have this motor, this is your motor, and your shaft is connected to this motor. And there is one, what you call as, there is one gear here connected. A gear here is connected. This is one gear. Let's say there is some gear connected here. This is gear. Let's say that is A, this is B, and there is one more gear attached somewhere here. Let's say one more gear is here. There is one more gear. Let's say this is one more gear that is called as C. And the thing is that you are delivering, so your motor is transmitting how much amount of torque here? It's transmitting 800 Newton meter, and it gets that gear P takes that 500 out of that. 500 is taken by gear B, 500 Newton meter, and the rest part of that 300 is taken by gear C, 300 Newton meter. And there's, after that, there is some extension of that shaft, and finally it's fixed here, clamped here. Let's say it's fixed here. So the dimensions here would be provided as this one, and this one. Let's say the length here is 0.4 meter. This is 0.6 meter, and this one is 0.3 meter. So I will say that this is ABCD, this is ABC, and this is your D. Now the thing is that it's saying that the motor exerts this torque. Exerts a torque of 800 Newton meter on the shaft. And the shaft is ABCD. Then after that, your diameter of the shaft is constant. Diameter of shaft is constant. You have to keep the diameter as constant function, and that phi or D, but we don't know the value of D. After that, you have one more thing given, that's that the theta permissible, that maximum theta you can have, angle of twist between A and D. That means total theta between A and D for the entire shaft, that should be less than 1.5 degrees. That means it should not be greater than 1.5 degrees. And we have one more condition, that maximum permissible stresses, shear stresses because of torsion, that is 60 megapascal, and G comes to be equals to 77 gigapascal. And you need to say diameter. What should the diameter of that shaft? For these set of conditions, what should be the diameter of the shaft? So based on these calculations, based on these conditions, there is some theta and there is some tau. If I say, so we have two conditions for calculation of diameter. Based on the equation, we have tau by J, G theta by L equals to tau by R. So for the diameter, we have either we can take tau max here, either we can take this part of the equation, or we can compare torque with this part of the equation, because we need diameter that is having in the equation of J, that's pi by 4, pi by 32 d to the power 4. So for the diameter calculations, you can calculate for either with respect to g theta by L, or you can calculate with the tau max by R. You have two different options. Let's say which one gives you stable results. Let's calculate first for your tau max. Let's say with respect to tau max equation, I would say, or with respect to tau max equation. If I write that tau max, this is your case one. If I take with respect to, if I use those torsion formula with respect to that tau max by R, that equals to 16. Directly I can say 16t by pi d cube. But that t should here be some value. So I would say there should be some t that's maximum. So how can I get this t now? Now the t I can get this t from the line diagram, from this line diagram. So your moment is anti-clockwise. So I would say your thumb points towards B. So your line diagram looks like this, 800. Then there is this is your, if I see this is your, in this way, this is your anti-clockwise 800. After that you have at the B, you have this clockwise, and similarly this one is also clockwise about this polar axis. So your thumb would point towards the motor side. So this one is your 500, and this one is your 300. And in this part there is no torsion. So if I make that diagram, of TMD, I would say there is a decrease of 600. Yeah, it's a positive because it is towards the section. If the torsion is towards the section, that is positive. So it's also we can say it's in the same direction of traverse. So I say this is positive 600, positive 800. Then after that it would decrease by 500. Net comes out to be 300. Finally it would go here to 0. So positive and 0, positive and 0. This is your TMD. So based on these two values, what is the Tmax we got? Tmax is equals to 800 Newton meter. So your Tmax is 800 Newton meter. (16 T by pi d cube). And tau max from the question, from the problem, it said that is 60 megapascal. 60 megapascal. And you solve it, you get a value of diameter that equals to 40.79 millimeter. So you got the first condition, first diameter. Either the diameter is 40.79 or the diameter is as per the second part of the calculations. So let's have the second perspective. That is, it's saying that the theta permissible between A and D, that should be 1.5 degrees. So if I write that theta A with respect to D, that is equals to theta AB plus theta BC plus theta CD. So I had to use those three equation parts. That should be less than or equal to 1.5 degrees. So I have this condition. I would be using that part now. So we have these different lengths, and I can use those. Equation in the equation. So I would write that for the first part. For the first part, I would write. For the first part, I would write that T. The value of T here was 800. I would write 800 Newton meter, and the length was equals to 0.4 meter. This was 0.6. This was 0.3 meter. So I would write TL by G. G is fixed for the entire section. So value of G and J is fixed. So value of G is 77. Value of G is 77 gigapascal. So I can keep that common. 1 by 77 gigapascal 10 to the power 5 megapascal, or Newton per meter square, Newton per millimeter square. So 77 into 10 to the power 5. Yeah, it's wrong. So 77 into 10 to the power 3 Newton per meter square gigapascal. So you have this G, and you have the value of J equals to pi by 32 d to the power 4. So you have this part that is common for the entire all those three sections. So this is TL by GJ plus second one is your TL by GJ and plus your 0 into 0.3. So you got this one, and that should be less than or equal to some degrees. how much degrees was given to you? 1.5 degrees. 1.5 degrees by 180 degrees into pi. So you solve this part, and you would get the diameter is the answer 1 by 4. That diameter equals to 42.07 millimeter. Now you got two different diameters. You had two options now. Which option should you prefer? Either you can take 40.79 or you can take 42.07. So I would say to satisfy all those both the conditions, such that to keep the theta less than theta permissible and to keep the tau less than tau permissible, I should prefer that diameter should be more. So I would prefer that diameter should be maximum of those two. So D should be maximum of those two. That is equals to 42.07. 42.07 millimeter. So this is your diameter, minimum diameter that is you should keep. So that is the end of this lecture. Hope you enjoyed those problems and my stucking in the torsional arrows. Okay, thank you.